Dear students, let us start today the new unit complex integration. Before seeing problems in complex integration, let us see few definitions. See, when can we say the curve is simple closed curve? So if it does not intersect itself, then the curve is simple closed curve. You can see here the curve which intersects itself, right? So it is not a simple closed curve. Okay, so the curve which does not intersect itself is called simple closed curve. And if the curve is not a simple closed curve, then it is multiple closed curve, right? Multiple curve. Next, let us see the third definition. When can we say the region is a connected region? So the region R is connected region if we take any 2 points in the region R, and if you connect them by a curve, if the curve lies entirely in the region R, then the region is said to be connected region. See, if you take any 2 points in R or connected by a curve such that the curve lies inside the region, then the region is said to be connected region. So if you take any 2 points, if one point lies in the region and one lies outside the region, then it is not a connected, right? It is not a connected region. If it lies entirely, if the curve lies entirely in the region R, then it is said to be connected region. Next, let us see simply connected region. So let us take a region R, and inside region R you take a curve C, closed curve C. If the region of C lies in the region of R, then the region is said to be simply connected region. The region of C lies in the region of R, right? In the region R, and hence it is simply connected. You can see it is multiply connected. It is whole. It is whole. See, this is the region R. It is whole, and this is multiply connected region. Example, you can go through. It is multiply connected region. Example, you can see there are many holes. There are many holes in the region, right? Which is an example of multiply connected region. There are many holes here. So there will be no hole in simply connected region, and there are holes in multiply connected region, okay? Which is an example. This scale is an example of multiple connected region. A simply connected region is one which does not have any holes, but multiply connected region has holes. So now it is ready to start the heading Cauchy's integral theorem. Okay. So after definitions, now it is ready to do. If we see these theorems, we can do problems. Cauchy's integral theorem or Cauchy's fundamental theorem. We say in short CIT. Cauchy's integral theorem. What's the statement of theorem? If f of z is analytic, we have already studied third unit analytic function. Okay, we know when can we say function is analytic. If f of z is analytic and f dash of z is continuous at all points inside and on a simple closed curve C. C will be given. Okay, C will be given simple closed curve. So being closed curve, C here you can see in all the problems C is circle. C is circle, okay? Circle with center and radius, you know. Circle whose center, radius known. So here a simple closed curve, which can be considered a circle. So if the function is analytic, if the closed curve, if you consider closed curve as mod z equal to 1. You know mod z equal to 1 is a circle, right? Mod z is modulus of x plus iy, which is root of x square plus y square. Mod z equal to 1 is root of x square plus y square equal to 1, or x square plus y square equal to 1. So mod z equal to 1 is a circle whose center is 0, 0 and radius is 1. Right? So here if you consider simple closed curve mod z equal to 1, then the function defined should be analytic inside and on the curve. Inside the curve as well as on the curve. And the derivative of function is continuous at all points inside and on the curve. Then integral over C f of z dz is 0. Then the value of the integral is 0, which is Cauchy integral theorem. State Cauchy integral theorem is very important 2-mark question. Okay. If f of z is analytic and its derivative f dash of z is continuous at all points inside and on a simple closed curve C, then integral over C f of z dz is 0. Let us discuss in detail the theorem while doing problems. Okay. See, so the theorem is for simply connected region. Okay, and the same theorem can be extended for multiply connected region. If C becomes C1, C2, C3, there are many inner boundaries. They are saying C is the outer boundary, C1, C2, Cn are inner boundaries. You can see this example. C is the outer boundary, C1, C2, C3 all are inner boundaries. Right? If f of z is analytic and inside and on a multiply connected region whose outer boundary is C and inner boundaries are this one, then integral over C f of z dz is integral over C1 f of z dz plus integral over C2 f of z dz up to integral over Cn f of z dz. Here answer is 0, right? Here we check. See, all the integrals are taken in the anti-clockwise direction. So while doing problem you can understand. Being I said C is circle, anti-clockwise direction is considered as the positive direction. That's why all integrals are taken in the anti-clockwise direction. Okay. Let us check in separate. For separate integral, whether the function is analytic and whether separate integral, let us see whether it satisfies Cauchy's integral theorem. And hence we verify answer is 0. Okay. Next, Cauchy's integral formula. It is analytic here, right? F of z is analytic region. Cauchy integral formula. Next comes Cauchy's integral formula. See, if f of z is analytic inside and on a simple closed curve C, and A is a point which lies inside C. A is a point which lies inside C. C will be given. Integral f of z by z minus A over C is 2 pi I into f of A, which is the statement of Cauchy's integral formula. We say CIF. You see the difference? There will be no denominator, and the answer is answer is 0. In Cauchy integral theorem, there is no denominator, and the answer is 0. In Cauchy integral formula, we have denominator term z minus A. This A should lie inside C. The condition is A should lie inside C, so that the value of integral is 2 pi I into f of A. Okay. If function is analytic inside and on the simple closed curve C, we need not verify whether it is analytic or not. Okay. Let us check whether the point lies inside. It will be analytic. If they ask you to do problem by Cauchy integral formula, f of z will be analytic. Okay. So we have to check whether the point A lies inside C or not. In case if it is z minus 1. If C is mod z equal to 2. So A is 1. So mod z equal to 2 is a circle with center 0, 0 and radius 2. Check whether this 1 lies inside the circle. If it lies inside the circle, answer is 2 pi I into f of 1. If it lies outside the circle, answer is 0. Okay. So we shall discuss in detail the formula in problems. Next, Cauchy's integral formula for the derivatives of an analytic function. If f of z is analytic, inside and on a simple closed curve C, and A lies inside C, very important, A lies inside C, then integral over C f of z by z minus A whole square. In Cauchy integral theorem, there is no denominator. Integral formula, we have simply z minus A. Integral formula of derivatives, we have whole square, whole cube, whole power 4, etc. So when it is whole square, it is 2 pi I by 1 factorial into f dash of A. Whole cube, when it is whole cube, it is 2 pi I by 2 factorial into f double dash of A in general. Okay. Anti-clockwise direction is considered as positive direction. That's why they said, okay, which is Cauchy's integral formula. Now we should do problems. Okay. So I stop here. We shall see in the next video problems.